When you think about the human mind, it often feels like there are these two gears, right? There's the fast, almost automatic snap judgment mode, and then there's the slower, more careful step-by-step thinking. In psychology, they often call this system one and system two.
System one is great for, say, recognizing a face instantly. Quick, intuitive.
Right. And AI has gotten remarkably good at those system one type tasks. Image recognition, basic translation, things that feel almost automatic.
But that's system two.
Mm-hmm.
The slow, deliberate reasoning needed for complex math or planning or writing intricate code.
Mm-hmm.
That's been a much harder nut to crack for AI.
Yeah, it's been a real bottleneck. It often limits AI from tackling truly new problems without needing loads of very specific training data. So today we're diving into some fascinating new research. There's a paper called Energy-Based Transformers are Scalable Learners and Thinkers.
Right, EBTs.
Exactly, EBTs. And they make a pretty bold claim that these models can actually learn to think more like System 2.
And the really interesting part is how they claim it happens purely from unsupervised learning. No special labels needed.
And crucially, they suggest it works across any kind of problem or data type, not just math or code.
Which, if true, would be a big step.
Yeah.
Moving beyond these very specialized solutions that often need that extra layer of supervision.
So our mission today is to unpack this. How do these EBTs actually work? How do they stack up against current models? And what might these early results tell us about where AI could be headed?
Sounds good.
Okay, so let's start with the core challenge. Why is System 2 thinking so difficult for AI models? What's the barrier when it comes to, say, complex math problems or figuring out novel programming solutions?
Well, as you said, System 1 is fast, automatic. It relies heavily on patterns learned from past experience. Familiar problems, quick answers.
But System 2, that's different.
Completely. It's slow, requires conscious effort, logical steps. It's what we use when facing something new, something complex, something outside the usual patterns or out of distribution, as they say in the field.
And many current AI models that try to do reasoning, they often just seem to, well, think for longer, right? Increase compute time.
They do, and sometimes that helps on benchmarks, but the paper points out some real limitations there. A lot of these models lean on reinforcement learning, RL, and RL tends to work best where you can easily check if an answer is right or wrong, like solving a specific equation or writing code that compiles.
Okay.
But try using that same RL approach for something like creative writing.
Yeah.
And performance can actually get worse. It's not universally helpful.
That's surprising.
And maybe more fundamentally, there's evidence suggesting this longer thinking through RL might not be creating new ways of reasoning. It might just be amplifying the model's existing tendencies, which kind of limits its ability to explore truly different solutions.
So it's not really deeper thinking, just
Yeah,
more of the same.
potentially, yeah. Even other approaches like diffusion transformers or RNNs face hurdles. Diffusion models often need some external judge to improve on System 2 tasks.
An outside verifier.
Right, and most modern RNNs, well, they can process more data over time, but they can't really just sit and ponder a single problem for longer without new input.
Okay, that sets the stage clearly. So EBTs come along and propose something fundamentally different, not just predicting the next thing, but learning to verify. How does that work?
This is the key shift, I think. EBTs belong to a class called energy-based models. Instead of just outputting a prediction, they learn to assign an energy score.
Energy, like physics energy.
Sort of analogous, yeah. Think of it more like an unnormalized probability or maybe just a compatibility score.
Okay.
It takes the input and a potential prediction and assigns this energy value.
Lower energy is better?
Lower energy means higher compatibility. It means the model thinks the input and the prediction fit well together. Higher energy means less compatible, more tension or uncertainty.
Okay.
So the whole prediction process gets reframed. It's not just a one-shot guess. It becomes an optimization problem.
Optimization, how so?
The model starts with a random guess, a random prediction. Then it iteratively refines that prediction, trying to adjust it step by step to minimize the energy score.
Ah, like rolling downhill to find the lowest point.
That's a great analogy. It keeps adjusting until it settles, until it converges on a low energy prediction. And because this whole process, learning the energy function and minimizing it, can be done with just unsupervised data.
It allows this kind of system 2 thinking to emerge naturally without needing specific reasoning labels.
That's the core idea.
Yeah.
And it makes the approach potentially very versatile. Language, images, whatever.
That feels quite different. It's like the model is actively checking and improving its own work.
Exactly. Evaluation is built in.
So how does this energy minimization thing actually lead to capabilities that look like human slow thinking.
Hmm.
The paper mentions 3 specific facets.
Right, these 3 aspects really highlight the advantages. First one is dynamic allocation of computation.
Okay.
Humans don't spend the same mental effort on every problem, right? Harder problems get more thinking time.
Oh.
Most standard AI models use a fixed amount of computation for every single prediction. But EBTs, because they iterate until they find that low energy state.
But can naturally spend more steps, more computation on the harder problem.
Precisely. They can effectively think for longer when needed, just based on the problem's difficulty as reflected by the energy landscape.
That's neat. What's the second facet?
Modeling uncertainty.
Yeah.
We humans usually have a sense of how sure we are about something before we act. For AI, especially with continuous data like images, modeling that uncertainty is tricky. But for EBTs, the energy value itself acts as an uncertainty signal.
Ah, because higher energy means less compatible, less certain.
You got it. A higher final energy score suggests the model is less confident about its best prediction. It has an internal measure of its own uncertainty.
Okay, dynamic compute, built-in uncertainty. What's the third one?
Verification of predictions.
Yeah.
Good thinking often involves checking your answer, right? Verifying a potential solution.
Definitely. Sometimes finding the answer is hard, but checking if it's right is much easier.
And that's often true computationally, too. Verification can be exponentially easier than generation. EBTs, by their nature, are explicit verifiers.
Because they are always calculating that energy score.
Right. At every step of the refinement, they have an energy score estimating the quality of the current prediction. This could be used to decide things like, okay, this is good enough, stop early, or, energy is still high, let's keep thinking, allocate more compute.
So dynamic thinking time, a sense of uncertainty, and built-in verification, that does sound like a richer process.
It's a more integrated approach, yeah.
But theory is one thing. How did these EBTs actually perform when tested? The paper compares them against standard models like transformer plus height on language and vision, right?
Yes, and the results show 2 interesting kinds of scalability. The first is learning scalability, which is about how well they learn during pre-training as you give them more resources.
More data, bigger models, etc.
And what's striking is that EBTs didn't just do a bit better. They showed a higher scaling rate than the standard transformer plus approach.
Higher scaling rate, meaning they improve faster as you scale things up.
Yes, across all the different ways they measured scaling. More data, bigger batch sizes, deeper networks, more parameters, more compute flops, even richer embedding dimensions. EBTs consistently scaled better.
Wow, across the board.
Across all measured axes, yes.
Yeah.
This suggests they're more efficient, getting more learning bang for your buck, whether that buck is data or compute.
And they mentioned being the first to outscale transformer plus like this without changing the tokenizer.
That's right, which implies the advantage comes from the architecture itself, not just processing the input differently. It suggests that at the huge scales of today's foundation models, EBTs could potentially outperform them significantly.
Okay, that's impressive on the learning side. What about the thinking scalability, the system 2 part during inference?
This is where those facets we discussed come into play. For language tasks, they found EBTs could boost their performance by up to 29% just by running more optimization steps, just by thinking longer.
29%, that's substantial. And standard transformers?
The transformer plus AVER, in contrast, showed basically no performance gain from just being given more computation time at inference. It does its fixed pass, and that's it.
So the EBT's iterative refinement really pays off.
It seems so. And that self-verification aspect, where they can generate a few candidate predictions and pick the one with the lowest energy, the benefit from that actually got better the more pre-training data the model saw.
Meaning the ability to think and verify improves with scale.
Exactly. It learns to be a better thinker and verifier as it learns more about the world.
Does it handle uncertainty well in practice?
Yeah, they showed that for text prediction. Easy, common words like the quickly settled to a low energy state.
High confidence.
Right. But harder, less predictable words like maybe fox in a sentence maintained a higher energy for longer. The model felt less certain, which matches intuition.
What about vision? Images.
Also strong results. In image denoising, they compared EBTs to diffusion transformers, which are state-of-the-art. EBTs significantly outperformed them while using, get this, 99% fewer forward passes.
99%? How?
It seems that optimization process is just much more efficient for that task than the standard diffusion process. Qualitatively, the images denoised by EBTs looked less blurry, too.
So better results, vastly less computation.
For that specific task, yes. And it wasn't just denoising. They also found EBTs learned better visual representations.
Meaning they understood the images better.
It seems so. When tested on ImageNet classification, the EBTs achieved something like 10 times higher accuracy than the diffusion transformers they were compared against, suggesting a deeper grasp of the image content itself.
Okay, those results are definitely eye-opening. Better scaling and learning, clear benefits from thinking longer, and verification during inference across different data types. So how does all this translate to generalization? The ability to handle stuff the model hasn't explicitly seen before. Maybe data that's a bit weird or out of distribution.
That's a key question. They found something really interesting there. There seems to be a strong linear relationship between how out of distribution the test data was and how much benefit the EBT got from its System 2 thinking capabilities.
So the weirder the data, the more the thinking helped.
Essentially, yes. The more the model was pushed outside its training comfort zone, the bigger the performance boost from using more optimization steps or verification.
That really aligns with how we work, doesn't it? We lean on that slower, deliberate thinking when faced with something truly novel.
It does map well to human psychology, yeah. And reinforcing this, they found that even in cases where an EBT model performs slightly worse than a Transformer plus after pre-training,
Right.
it often still achieved better results on downstream tasks,
Yeah.
especially the out-of-distribution ones.
Interesting. So the way it learning to verify seems to inherently promote better generalization, even if its raw pre-training score isn't top.
That appears to be the hypothesis supported by these results, yeah. Learning to verify might be a more robust way to learn representations that transfer better.
Now, are there any downsides, limitations mentioned?
Oh, sure. It's still early days for this approach. The paper notes that EBTs do introduce more hyperparameters, more knobs to tune during setup, which can be complex.
Okay.
And currently, both training and running inference are more computationally expensive per step than standard transformers. That 99% reduction in steps for denoising was great, but each step might cost more.
A trade-off there.
Right. They also mentioned struggling a bit with highly multimodal distribution situations where there isn't just one good answer, but maybe several very different equally valid ones.
Makes sense if it's trying to find a single low energy point.
Potentially.
Yeah.
But despite these limitations, the scaling trends they observed, even at the smaller scales they tested, are really promising. They strongly suggest these benefits could become even more pronounced as models get scaled up towards the size of future foundation models.
So wrapping this up, it feels like these energy-based transformers offer a genuinely different path forward by shifting the focus from just prediction to optimization and verification.
They unlock these capabilities that look a lot more like human slow thinking, dynamic computation, handling uncertainty, self-verification.
And the results suggest they scale efficiently, generalize well, especially to novel situations, and can model that uncertainty across different kinds of data. It's quite compelling.
It really is, and it makes you wonder, doesn't it? If we could have AI that genuinely engages in this kind of adaptive, deliberate, System 2 thinking. Think about the really big, complex problems we face. Proving some long-standing mathematical conjecture, designing a radically new material, maybe even tackling complex diseases. If AI could truly think deeply about these, how much compute would we be willing to give it? What new frontiers might open up?